Hello and welcome to Mr. Queen Science. Tonight we are going to be looking at our AP chemistry review with that AP exam coming up in about 6, 7 weeks, but we still got plenty of time. Tonight we're going to be looking at week 2, which is based on unit 2 of the AP curriculum, which is molecular and ionic compounds, specifically their structure and function. So let's get it. All right, so quick overview like we did before of what is this unit all about. Again, these little guides again are designed for your teacher, but they can be really helpful for you as you're moving through the material as well, just to make sure that you really have touched on all the topics. They also tell you pretty interesting stuff like how much of the test it's going to be on and about how many class periods your teacher should have talked about it. Now, again, these are obviously all for teachers, like that's what they're targeted towards, but hey, they're being transparent with this information. So it does give you an idea of about probably maybe how much study time you want to direct towards it as well and the proportion that's going to be on the test. I also like to know these kind of recommended practices that go with them. Again, probably because I'm a teacher and I'm kind of geeking out on it, but they also do give you a little bit of insight on the kind of skills and questions that might be asked about these. Of course, any kind of question is fair game for any single topic. Gives you a little bit of an idea though. This unit does have a couple points of argumentation that you're going to see a lot. So that could be something common on an FRQ or a multiple choice where they want you to explain why it's this resonance form or explain why it's this VSEPR or argue why one form is better than another. There's also a good amount of model analysis and representing data, which is of course makes sense, right? This is pretty much all about modeling and being able to explain it using different types of models. So let's get started. The first thing we're going to look at tonight are types of chemical bonds. Oh, but before that, each week I'm going to try to give you a AP study tip from my own repertoire of tips. Last week was supposed to be know and practice your mental math. That might have got a little bit swept under the rug, but that's perfectly fine. Go back and practice your mental math. That's going to be absolutely critical for your multiple choice section on the AP Chem exam. You got to be able to do those without a calculator. Today's AP study tip is know your nomenclature. Some teachers make you take a test or a review at the beginning of the year. Some of you guys might be self-studying, or you just had a teacher who kind of let you off the hook. There's no excuse at this point. You need to remember how to name ionic compounds, how to name covalent molecules, acids. There is a naming convention as well. How do you know when it's hydrochloric acid? How do you know when it's hydrochlorous acid? How do you know when it's not hydrochlorous, just chlorous acid? And how do you know when it's chloric acid? All right, so there are rules for that. I'm not going to go over all of them here. There's lots of awesome nomenclature videos, and there's lots of awesome nomenclature resources. Also, of course, you should know your polyatomic ions. You don't need to memorize all the other metal ions. I guess it could be helpful. It won't hurt, but just the polyatomic ions you definitely want to know. There's probably even like a greatest hits list that you could probably get away with, like nitrate, sulfate, sulfite, chlorate. Again, there is some patterns here. There's like I've heard of like this Nick the Camel thing, which sounds cool because my name's Nick, but I don't really know it too well. I just brute force memorize them. So I recommend that you do the same. Oh, this link doesn't work on a YouTube video. I got to figure out how to make that work. But I do have some pretty cool resources with this. So if you are watching this video and you are struggling with nomenclature and you don't, or maybe too embarrassed to ask your teacher, or you don't know where to go because you've never used Google before, message me, reach out, and I will share some of those resources with you. So let's get into the actual topics now. Okay, so our first topic tonight is chemical bonds. Chemical bonds. So I wanted to point this out because I see it on a lot of resource materials online, not necessarily for AP, but just for chemistry in general. This thing right here, where they say there's 4 types of bonds. I'm like, whoa, this is not a bond. This is like a total imposter bond. Okay, so it is an interaction. If you're going to use the word bond just to mean some kind of interaction between substances, then it's going to be okay. But the difference, the hydrogen bond, is it is an intermolecular force. That means it's between molecules. When we're looking at chemical bonds, we're typically thinking about the bonds in between atoms in different kinds of compounds or atoms in metallic solids, not in between individual molecules. So don't get it twisted. A quick review: ionic bond involves a transferring of electrons. One element is just so greedy for those electrons that it basically snags them. Like you see here, sodium, whoop, got that. And it generates an ion, a positive and negative charge. And then the bond is actually the attraction between that positive and negative charge. We'll get into kind of the electronegativity of this in just a minute. Covalent bonds are genuine sharing of electrons, they're doing their best to share, we're going to see that they're not always very good at sharing. Sometimes there's one atom is a little bit more electronegative than the other and makes that an uneven sharing, which will result in a polar molecule, which we'll explore soon. And then finally, we have the metallic bond. If hydrogen bond's the imposter, then I feel like metallic bond's kind of like the weird stepchild of the bonding family. It's a little bit different. The way that its electrons are distributed is more delocalized, and they're not directly being shared or transferred to any specific atom. So that's essentially your chemical bonds. Interesting enough, the suggested skill here is argumentation. So be able to make a scientific claim. Like, what does that even look like? I'm still trying to figure out that myself. But essentially, you might have to make some kind of claim about where the electrons are located, how they're bonding, the differences in bonds, so on and so forth. Okay, so I said I was going to get a little bit into the electronegativity of bonding and what that even means. So yeah, let's figure that out. So electronegativity, we looked at that in the last video, and it is a kind of arbitrary scale of a measurement of how, I like to think of it as this, how greedy an element is for electrons. Now, that's not the technical definition. I think it's its ability to attract electrons. I might be confusing that with electron affinity, but essentially just think that this element really wants to pull in those electrons, and we can use Coulomb's law to explain why. It usually has something to do with the nuclear charge of the nucleus, and also how the distance, the overall size of the atom. So I think we looked at that last time, Coulomb's law, right? Q1, Q2 over R squared with a K, and I kind of simplified it down to say all I really care about is the nuclear charge over the distance. Essentially, electronegativity is going to be how strongly they are pulling on those electrons at any given time. So what that means is when two atoms bond and essentially share electrons to some degree, the greater the difference in their electronegativity, the less equal that sharing will be. So imagine a little weak guy over here, and he can barely pull the bond compared to this big, strong fluorine. He's not happy. And this guy's like, oh my. So in this kind of situation, the electrons would not be shared freely. Think of it as a tug of war. Fluorine is the absolute buffest. He is the king, or she is the king of electronegativity. And the general trend is as we go this way, francium is the lowest. Now, anytime we have two electrons or two elements that are two atoms that are binded together and they are the same, then that means they're going to have the same electronegativity. That's going to be an equal pull. So even two fluorines, they're pulling it for their dear life. That covalent bond is still nonpolar because they are pulling an equal amount. However, if we take something like carbon and fluorine, that's a very what we call a polar covalent bond, because that fluorine is really pulling those electrons a lot more away from carbon. So we call this a polar covalent bond. And if we get really extreme, if we do something like lithium and fluorine, we see that there's a very large difference. That's actually fluorine's pulling it so hard that it steals it, it transfers it, and it creates an ionic bond. So just a couple disclaimers about this whole bonding using electronegativity to define it. You may have learned like, oh, an ionic bond, which is great. An ionic bond is metal and nonmetal, which it usually is. And a covalent bond is two nonmetals. And that's generally the case. But what scientists have actually seen is that every polar covalent bond is slightly ionic in nature. It's more of a spectrum of bond characteristics. So we could say it's more ionic in nature or covalent in nature than actually there's a strict line. Because I do know some teachers say, oh, if the electronegativity difference is less than 0.5, it's nonpolar. If it's less than sometimes these numbers seem arbitrary, less than 1.7, then it's a polar covalent. And if it's greater than 1.7, then it's ionic. You're not going to have this table on the AP exam. When you're practicing doing your homework, maybe get out this table so you get the hang of it. But what you really want to get is a general sense of where the high electronegativity is and the low electronegativity is. So fluorine, again, is our kind of king of electronegativity. The further you get from fluorine, the more the more polar that bond's going to be. The one thing that I would point out and say that is worth sort of memorizing is that carbon and hydrogen, when they form a bond, although there is a slight disparity in electronegativity, you would expect carbon to kind of be tugging those electrons a little bit more because it is a little bit more electronegative. The difference is relatively small. It's less than 0.4 electronegativity. So we generally say CH is nonpolar. This is going to be really important next week when we get into IMFs. It's also important when you start looking at bigger molecules like organic molecules. And although I know organic is no longer on the AP exam, understanding it just a little bit can make some problems a lot easier. Okay, so with that, it's the last thing I wanted to show you. I'm not going to just sit here and read it. If you need to review this, then pause the video and watch it, or find a cool table in your book. Or even better, this is why I'm really showing you this, because this is a study technique that I personally think is very useful. So a lot of educational research has shown that the average person requires about 8 exposures or interactions with material in order to kind of start incorporating it into their longer term memory. Now, I know you're an AP Chem, so you're not average. You don't need to see it 8 times. You only need to see it 6 times. Either way, the more times you interact with something and the more different ways you interact with it, the better it is going to fit into the association network in your own brain. So I like this technique because most of us don't take notes in these nice organized graphic organizers. What you can do is go back through your notes or your teacher's slides or your textbook, and you can actually sort of break it down. You can take the information you have and organize it into a table like this. So first of all, it's forcing you to actually interact with the data actively, not just passive. You're not just sitting there going, do, 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 do. I'm just reading, oh yeah, formation, source, melting point. Because some of that will stick, but it won't all stick. When you actually have to like work with it, and if you don't like to write it, then type it or however you want to represent it. So not only are you being active when you make a table like this, you're also creating basically a reference tool, because now all the information, the comparing and the contrasting, is so much easier. If you encounter a question that says to compare, contrast, or to discuss or describe, you kind of have been studying that. Oh, I know how the melting point goes across these different types of materials. I understand conductivity against all three. I can visualize that chart. I remember making that chart. So again, I'm showing you this more as a study technique. If you have never seen this data before, of course you should probably try to learn it. And there's a little bit more information about these compounds as well that you can research, make it a bigger table. But just wanted to introduce this technique of using graphic organizers and creating them on your own. It is so much more powerful. Same thing with like mnemonics and other memory techniques. When you create them on your own, they have more meaning to you. They can fit more deeply into your network of associations, which is essentially what is the basis of what you call knowledge. All right, so next topic right there. I know we went through that quick. I don't want to talk about chemical bonds all night. Okay, intramolecular force and potential energy. So intramolecular force is the force between molecules. Okay, the force not between atoms in a molecule, if that makes sense. So this is like the force of bonding, essentially. So they love showing this diagram, and I know so many students who like panic when they see this one. They're like, what does this mean? Well, like any diagram, let's read it. And I think what throws a lot of kids off or students off is that the potential energy is negative. And they're like, how the heck is that happening? It's relative to the fact that if they were not interacting at all, which is represented right here. So in this part of the graph, this bottom part is the distance between the nuclei that we're looking at. We see that they're so far apart, they actually no longer have any kind of electrostatic attraction, either repulsion or attraction. So we would say that their potential energy is basically zero. They don't have any kind of interaction with each other. However, as we move as a smaller and smaller internuclear distance, we're going to go all the way to the extreme over here. These two atoms are so close together and they hate it. They are repelling each other. So that's why we have a really high level of potential energy, which corresponds to repulsion. But there is a sweet spot. And every molecule or every bond kind of has a different sweet spot where the bond energy, it's basically where they like to be, where they're going to have the lowest potential energy. Most things in the universe are trying to get to this nice spot of low potential energy based on their position. So this represents the internuclear distance, the distance between the two atoms where it has the lowest energy. And that's where the ideal bond length is. A little bit of elaboration on this. In a covalent bond, so what's going to determine like how tightly covalent bond atoms are bound together? Like what's going to determine their internuclear distance, which is going to be the bond length, and also the bond energy. So you can usually use Coulomb's law, right? Oh, I forgot how to spell suddenly. That's wrong. Okay, so you use Coulomb's law to actually help you decide how strong the force is going to be between those two atoms, which will allow you to make estimations about the bond length and bond energy. bonds with a higher order. So if you have like a C bond and a C double C bond and a triple C bond, this one is going to be the lowest energy and the longest distance, right? And this one's going to be the highest energy and the shortest distance. Now, of course, you can't directly compare bonds between different atoms like this, but within the same atoms, you're going to be able to see that the bond order corresponds to the amount of energy in that bond, as well as the distance of that bond, the length of that bond. Okay, I think there's one more thing here. Let me see. Oh, the other thing that determines the length of these bonds in a covalent molecule, besides Coulomb's law, like how much they are actually attracting each other, is the size of the atom. So I guess that's what I meant by Coulomb's law. So molecular, how tight the bond is not just directly based on atomic radius, but it is somewhat based on that because it limits how close they can get together. Whereas ionic bonds are a little bit different. So, whoops, let's not go there yet. So that's covalent bonds. Ionic bonds, like what determines how tight ionic bonds are linked together? And we'll explore this some more when we talk about ionic bonds and lattice energy. But it has to do with two things. It has to do with the charge between the ions. With greater charges would be greater force of attraction. So they will most likely be even closer. They're kind of pulling each other closer. And second of all, it's going to be based on the size of the ion. So bigger ions can't get as close together as smaller ions can. And we're going to see how that relates to lattice energy in just a little bit. So I tried to sneak in a few practice questions along the way, not that many, but a few. So let's look at this one real quick. I don't know where this came from. This is just a random question, but it seems AP appropriate. The potential energy as a function of internuclear distance for three diatomic molecules X2, Y2, and Z2 is shown in the graph above. Based on the data in the graph, which of the following correctly identifies the diatomic molecules X2, Y2, and Z2? Okay. Ooh, geez, this seems so hard. How are we going to do it? Well, let's look at our graph. We've got internuclear distance. We know that has to do with the bond length. And then we also have some action going on with the bond energy. All right, so we haven't practiced Lewis structures yet, but we're going to need to use them right here. So I'm going to quickly whip up some Lewis structures. If you don't know how to do that, we are going to talk about it a little bit later. Okay, so there's our H2, our O2, and our N2. Now, I already see right here, this is going to be giving me a big hint. I see, whoa, that is a triple bond. That is like extremely high potential energy. I don't care what elements it's between. So I'm already going to jump in right here and say, dude, that's got to be N2. Now, I would anticipate the triple bond to be shorter than the double bond or the single bond. However, I'm not comparing it to other nitrogen atoms like this. I'm comparing it to these hydrogens and oxygens. So there's more things at play here besides just the number of bonds. There's also the size of the atoms that's going to impact the energy a lot too. So since hydrogen is really small, it makes sense to me that, hey, it could actually have a pretty small internuclear distance since the atom itself is only has that one energy level. It's able to get much closer. So it's a little bit hard for me to determine, but I'm going to guess that that's H2. And I'm going to call that O2 because it's all that's less, which makes a little bit of sense to me because it is a longer bond than the triple bond, which makes sense. And because it has roughly similar distance because they're both the second energy level. And then the second thing you want to look at is, like we said before, bond order. And the other big thing is atomic radius or atomic size. So since oxygen has a larger atomic radius, it makes sense to me that it's a little bit bigger. Also, since it's a double bond, it makes sense to me that's a little bit bigger. And it also makes sense to me that it's a little bit less energy. So let's see. Is that an option? I really hope it is. H2, Y2, O2. Okay, I would choose A. I did that one on the spot. I really hope it's correct. Most likely is. All right, let's move on to the next topic for tonight, which is ionic bonds and compounds. Okay, so ionic bonds and compounds. Oh, we've got a little exception statement right here on the side. It says knowledge of specific types of crystal structures will not be assessed on the AP exam. Whew. So we don't need to know about any crazy crystal geometry. Now, most of your teachers probably didn't even talk about that, but in case they did, you can basically let that one go and save it for college. Okay, so in ionic bonds and compounds, like we said before, and we see in this diagram here, this chlorine is so electronegative. It's so greedy for electrons. It's actually going to not just only share it unevenly, it's going to steal it completely. And it's going to happen in both of these compounds. Now, usually you show like an NaCl, but I wanted to look at something different because sometimes students are like, well, how does that apply to these other ones? So we can see same thing, it just requires 2 chlorine to make this happen. Now, magnesium has 2 electrons that it can give away very easily. They're in the outer valence shell. We talked about ionization energy a little bit last time, and we saw that elements such as magnesium, their first 2 ionizations are pretty easy to occur. Like they're pretty low ionization energies. So what happens is magnesium loses 2 electrons, so its charge goes up by 2, and chlorine gains an electron. So now there's an attraction between this negative and this positive, and this negative and this positive. And that's essentially what an ionic bond is. So how do we always know like exactly what to have for how many bonds are being made in an ionic compound? I think we practiced this last time, but one more time real quick. So magnesium, with the periodic table, you should be able to identify that the most commonly generated ion by magnesium is the 2+ ion. And for chlorine, it would be the Cl-. So we do this little crisscross shortcut thing, which is essentially just making sure that the formula unit, which is like the chemical formula of the ionic compound, is in fact stable and it is electrically balanced. Okay, so that's ionic compounds. Real quick, a little bit of the characteristics of ionic compounds. I know it was on an earlier slide, but we kind of breezed by it. You do have to remember, if you hear something called a formula unit, like what are they talking about? A formula unit for this compound would just be NaCl. So you have, what I was trying to say, you have to remember is you're not going to find like 1 sodium and 1 chlorine and the rest of the universe is empty. That would be cool. That would be a nice little binary compound. But in reality, we have millions and thousands and bajillions and moles of atoms. So what actually occurs here is something like this. Instead of writing Na5000 and Cl5000 or 5 mole or however many there are in that crystal, we just write NaCl. It's kind of like formula unit's kind of like the empirical formula in a way for ionic compounds. Don't quote me on that. I don't know if that's a crude misevaluation. Okay, so what happens here is we have an interaction there, and we have an interaction between this, and we have an interaction between this positive and negative. So hopefully what you're starting to see is there is a lot of interactions here. And in reality, it's 3D. So they're going forward and backwards and into the page and out of the page and side to side, left to right. There's lots and lots of interactions. So this makes ionic compounds in general very kind of, I would say, strong. Not strong, like they won't break. I guess very hard, very high melting points. It's right. We don't usually just like boil salt, just pure salt. And this has to do with their interactions between them. So yeah, that's most of what you need to know. It also is the reason why they're very brittle. Imagine if you applied a force right here, right? And we just somehow had the ability to just scoot every atom over 1. Well, first of all, this substance would really, really, really resist that. I wouldn't want that to happen. But imagine if we were able to do that. So we've got an Na+ here instead, and a Cl- here, and an Na+ here, so on and so forth. What's going to happen in that moment? Well, holy crap, there's going to be a huge repulsive force between these 2 positive ions and between these anions and between these. So it's going to be brittle. It's going to shatter. It's going to display the properties of an ionic solid. Gave us a little bit of a chance to explain the actual molecular or compound geometry behind some of these traits. All right, so next up is the sort of, like I said, the weird stepchild of the bonding family, and those are metallic bonds. Metallic bonds, oh my gosh, every teacher and college board, everyone knows to say this, sea of electrons. So essentially a metallic bond, it's like the communism of bonds, sort of. They're like really open and free, loving and sharing of their electrons. They can just move all however they want between all the other atoms of the same substance. So metals don't hang on to their electrons that tight when they're in this pure metal state, when they have metallic bonds. Sometimes this is referred to as delocalized electrons, and it's represented like this. Because these electrons aren't bound kind of in place, it makes it, if we apply a force here, unlike the ion where it would shatter, it's actually going to be able to bend. So we might call that it being malleable. It's ductile. It means it can be bent. It can be made into wires. It can be flattened into sheets like foils. Yeah, lots of interesting properties. It's also a very good conductor because not only can the electrons can kind of be a little bit free to scoot on through the material, so it's conducting electricity. They're also very good at conducting heat. Let's see, what else can we say about metals? Heat and electricity. Oh, they also have what we call luster. It's like that shine. And that again has to do with their structure. So all of those characteristics that you see can always be brought back to the structure. The main, like if you learn nothing from this topic, just know sea of electrons and the basic traits of. Okay, so we got some more practice questions. Cool. So of the compounds listed, which would have the strongest lattice energy? So I did mention lattice energy and the strength of the intramolecular forces in ionic compounds, but sometimes it's hard to translate those concepts into actually how to solve a problem like this. And I feel like there's like always like one question like this on the AP test. So we want to make sure we get it right, especially these questions that have a systematic approach. So how do we determine lattice energy? Well, what even is lattice energy? So it's the energy in that weird grid thing that we were looking at earlier. It's the potential energy of the positions of the grid of an ionic compound. So how do we determine which one has the strongest lattice energy? Okay, this is pretty easy. We can follow this. So if you struggle with this, here you go. Here it is. Number one, the charges of the ions. Number two, the size of the ions. So the number one thing that you're going to use to determine how strong the lattice energy is the charge of the ions. We can use Coulomb's law to actually break this down with like a little bit more math, but just believe me, the charges of the ions, that's always going to push you towards the one that has the strongest lattice energy. If it's a tie, like if you have NaCl and NaF, right? They're both ions plus one, negative one. So you've got the same charges. Then we go to the size. Right? We don't go to the size first. Do not make that mistake. We go to the charges first. Then the size, the smaller they are, then that means they're going to be closer together and they're going to have more strength in their lattice. So for this one, we've got what? A +1 and a -1. We got a +2 and a -2. We got a +1 and a -2, and we got a +2 and a -1. So the only one that has, or the one with the strongest difference in the ions would be this guy, +2, -2. So MgO is our strongest lattice energy. All right, second question down here. Which of the following pure substances will conduct electricity? So we didn't talk too much about this, but let's go over it real quick. Usually covalent compounds, they kind of suck at conductivity. They're not very good about it. There are some things like semiconductors and stuff, but don't worry about it for this course. Ionic compounds. So, well, what makes something conduct electricity? It needs to allow electrons to flow through it. That's what electricity is. It's a flow of electrons. So ionic compounds can do that when they're actually in their ionic form. But when they're sort of locked in that solid form, all the electrons are busy being attracted attracted to all the other ions around them. So they don't got time to be letting no electrons scoot around. They're locked in place. So ionic compounds are not conductive as solids, but as a liquid or in solution, so aqueous, the AQ thing, they are actually really great conductors of electricity. So that's why when you dissolve salt in water or you're working on electrochemistry later in the course, you're going to see that ions are actually essential for conducting electricity. Finally, we have metals, right? Metals are generally good conductors. Some are better than others, of course, but for the most part, we can kind of go with that. So let's look through here. Which of the following pure substances will conduct electricity? We got K2O. It's ionic, but it says it's solid. And we know ionic compounds, not good conductors as solids. Okay, next up, we got lithium bromide, another ionic, and it's aqueous. Hey, that's pretty good. So I personally would just put that as my answer and move on and maybe put a little star that said, hey, I didn't check C and D, but I at least knew this one. I'm going to move on. That's my strategy on these. I know some people are like, read every answer choice and analyze each one, break it down. I personally feel like with the AP Chem test, you just want to like start racking up points. Like just go through the whole test once, answer all the easy questions, go through this test a second time, answer the slightly harder ones or the ones you wanted to double check, and then go through a third time and finally answer those ones that feel a little bit impossible. Now, a lot of my students were like, hey, H2O, dude, what do you mean? H2O clearly conducts electricity. Well, I did say a pure substance. And to be honest with you, distilled deionized water is not going to conduct electricity. You're like, what? Why did my mom tell me not to take the toaster in the bath? Well, that's because first of all, your water in your bath is probably not pure, but even if you purified it and it's really perfect distilled slash deionized water, if you got into it, the salt from your skin would probably get in the water too. So don't go in the bathtub with a toaster. You can test this out other ways. You can buy like a conductivity meter and put it into a cup of distilled water. All right. So we have one more topic to discuss in metals, and that is alloys. So a pure metal, we discussed already a little bit about its structure and its properties. Let's just call this iron. Alloys are essentially mixtures of a metal and some other element, oftentimes a metal, that, how would we say this? They mix together to essentially give a compound with, or a material with, new properties, which is really cool. You can combine, let's say, something zinc and copper. I think that, I'm pretty sure that that is brass. I think that's brass. So zinc and copper. And when brass has a different color, a different properties and everything than zinc and copper alone. So this first example I started to fill in here, zinc and copper makes brass, is an example of something called a substitutional alloy. So this usually occurs, like, let's say the red ones were zinc. So again, I don't know the exact structure of brass, so don't like quote me on it. Or maybe it's bronze. I don't know. We're just going to go with brass. Okay, so when the atoms are roughly the same size, then it usually creates what we call a substitutional alloy, which means where some of the zinc atoms are located, they're out, and now a copper is in that spot. Okay. Usually most alloys, the properties that they gain is they usually become less malleable, more rigid. They essentially become stronger and harder. And you might say, well, why is that the case? Well, these nice little perfect grids where things could kind of slide by each other, this matrix of atoms in three-dimensional space, it's now disrupted a little bit. So it can't bend and slide and move as easily. Now there's a slightly different size atoms in there that are affecting it. Also, of course, these different atoms might have different valence electrons and different orbitals, maybe not different orbitals, but different valence electrons that might have an effect on their property. Now down here is an interstitial alloy. So a really classic example is iron and carbon, which makes steel. If you know anything about steel, it's way, way, way stronger than iron. And here's why. The carbon form an interstitial alloy, which means they kind of hide in these little pockets in here. And they make it even more challenging for these sheets, these kind of rows of iron to slide past one another. In fact, if you look at this in 3 dimensions, you'll see it completely disrupts the matrix of the iron atoms. So that's what gives it its additional properties. And finally, you can have something where you have iron and carbon and maybe throw in some chromium, and now you've got stainless steel. Ooh, shiny. And this has some properties of both. Not only does it have the interstitial strength from the carbon, it has a little bit more luster from the chromium. So what you really need to know about alloys are, what are the two types, substitutional and interstitial? When do they come up? Well, substitutional is when the atoms are roughly the same size, and interstitial is when one is substantially smaller than the other. And finally, what are the properties? They become, in general, stronger and more rigid than the metals on their own. Okay, so one quick question about it. And this question is honestly more about good test taking than it is about answering the question. So which of the following diagrams best depicts an alloy of nickel and boron? So I remember an alloy is when it's like a metal with some of them are switched. Okay. The first thing I'm going to eliminate is this one. Why are there negative and positives? This is an ionic compound. This is not what we want. And this one, that's not what I learned about as a metal. That just seems like a binary compound all lined up, probably a covalent one, because it's just repeating over and over. That's not what an alloy is about. So these two are my choices for alloys. I have one atom, I don't know what it's represented by, and there's some kind of filling, and another atom, another one where it has bigger atoms and smaller ones. So what I have to ask myself is, are nickel and boron the same size? And if I go to the periodic table, I'm going to see that no, boron is much smaller than nickel. It has fewer energy levels. It has fewer protons. It's going to be not that the protons are what's causing it. Sorry, I didn't mean to say that. It has fewer energy levels. It's a smaller atom. Based on our basic atomic radius stuff, we know that. So it's going to be this answer right here. It's not going to be this. So it's going to be what we call an interstitial alloy, not a substitutional. Now, actually, I doubt you'll see these type of diagrams I personally think they're not good representations of alloys because they don't show the complexity of the 3D shape. And I'm pretty sure AP feels the same way. I remember reading something a couple years ago that they're trying to move away from using these type of alloy diagrams. All right, let's keep rolling. This is a long unit, so we got to move fast. All right, a sample of a hard, solid, binary compound at room temperature did not conduct electricity as a pure solid, but became highly conductive when dissolved in water. Which of the following types of interactions is most likely found between the particles in the substance? Okay, so I hear the word hard. So I'm like, okay, it's probably a metal or an ion, but I've heard of covalent bonds that could be hard too, like solid carbon or something. So maybe that's not going to help me too much. It's a binary compound. All right, so it's probably not metallic unless it's maybe an alloy. It did not conduct electricity as a solid. Okay, so it's definitely probably not a metallic bond between particles in the substance. Okay, it's probably not hydrogen bonds because that's not between particles in the substance. It's between molecules in the substance. We're getting kind of narrowed down here, but the real giveaway is it's very conductive in water and it's not very conductive as a solid. So clearly the answer is an ionic bond. This is one you should be able to answer, I'd say, in like 20 seconds or less. So you can then save your time for those super annoying acid-base questions. Oh, we're already here. Okay, Lewis structures. Ooh, everyone loves a good Lewis structure. So I'm not going to teach you how to draw an entire Lewis structure. This is a skill. These are one of those skills that you are just essential to have. So as I talk about it, I'll draw one just so you know. But so right, we got NH3. So after you've been drawing these for long enough, they just kind of just come naturally. I don't like to do the little dot thing. I like to draw mine as bonds because I'm a messy person. And when I draw that many dots, but this is the Lewis structure for NH3. It's essentially a model that represents how the bonds are organized. Now, again, it's a model. All models have limitations. It doesn't tell us the whole story. There are a few rules, though. We want the total number of electrons in here to be equivalent to the total number of valence electrons, since those are the ones participating in bonding. Okay, so again, hopefully you understand a general strategy to doing these. Count up the valence electrons, make sure that they get all spaced out. So the big ideas are valence electrons and octets, right? And the valence electrons thing never really fails you. The octets we're going to see is only a limited time offer. But my advice to you, and I know this doesn't work for every single one, it's not the official rule of how to do these. I'd say formal charge is the official rule. But I always teach my students this to just give them a general idea of how to construct the basic skeleton of the molecule. Sometimes you try this and it fails. That's fine. There might be an alternative. But if you're just trying to get the right structure and not think about all the possibilities, then this is a pretty good tactic. So in general, hydrogen and the halogens like to make one bond. Oxygen and everything in that family, like sulfur and so forth, like to make two. Nitrogen and its group moving down, like phosphorus, like to make three bonds, and carbon, due to the number of valence electrons available, tends to make four bonds, as does silicon. So I would used to say 1, 2, 3, 4, honk if you love Lewis structures. Yeah, I know it's kind of corny, but it does give you a place to kind of start. There's other strategies that say put the least electronegative element in the middle. What I realize is you almost always want to just put carbon in the middle. There are alternatives to this, but it's usually the best strategy. The more bonds it can make, try to put it more towards the center, and it'll usually have a payoff. Okay, you are also allowed to do like double bonds and all that kind of stuff. Again, this is like a super foundational concept. If you're really struggling with Lewis structures, there's tons of resources, and you probably just need to sit down and brute force like a bunch of them. Just look at it. Actually, what I would do, I would combine this with VSEPR, polarity, and IMF. Do it all at once. And if you're like, what do you mean? Message me. I can give you worksheets that basically just have like a compound, space to draw it, what's the polarity, what's the IMF, what's the geometry, all that kind of stuff. And I'd say that's the best way to do it. Get to the point where it's like natural, where this is like the thing you're like, yes, I get to draw a Lewis structure. This is so freaking easy. This is free points, because it really should be free points, unless you get some really crazy one. Now, one thing I'm going to throw in here before we get into the complexity of like formal charge and resonance is this is for ions too. So polyatomic ions have Lewis structures and they follow the same rules. The only difference is you got to kind of address the charge that's there. Now, I noticed that when we get to ions, that's usually when we start breaking this honk rule. Hey, but that's okay. So this is going to guide you through like most basic ones, or it's going to get you started. Sometimes you're going to modify from there. But let's look at an ion just as a little quick practice. Let's see, what do we like? What's our favorite ion of the week? I don't want something with a resonance structure. Okay, so we will do NH4 plus. Okay, so nitrogen has 5 valence electrons. We have 4 hydrogens, which would be 4 valence electrons. And the positive sign means we're missing an electron. So we got -1. So all together, so we're missing an electron. Sorry if that throws you off because of charge. I got 8 electrons I'm working with. So I'm going to draw my nitrogen, and 1, 2, 3, 4. Now I know nitrogen doesn't typically like to make 4 bonds, but it can live with itself. And overall, this whole thing has a positive charge. So I count up my electrons: 1, 2, 3, 4, 5, 6, 7, 8. I've got my 8 electrons. The octets are, for the most part, met. And that's it. Oh, and I put my charge on the outside. I usually bracket this as well. All right, so that's a basic Lewis structure. Again, use this honk strategy to get you kind of started. If you have trouble with them and you don't know, like, for example, like you see something like this, you're like, oh, which one's the central atom? I don't know what to do. Oh, carbon, always put in the middle. 2 bonds to oxygen because that likes 2 bonds, and 1 bond to each hydrogen because hydrogen likes 1 bond. Bam, I'm done. I didn't even have to count my electrons. Of course, the more you study chemistry, if you take organic chemistry and things like that, these start to just become second nature. So practice, 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 practice until they're easy. And then realize that there's a bunch of exceptions to all the practice you did. So there are a couple molecules that tend to generate what we call you might call electron deficient molecules. They have an incomplete octet. These are kind of like really exceptions, and they have to do with, like, I'm pretty sure, with the size of the atom, the central atom, and the ability of it to bind very closely because it only has that one energy level. So you might see BE can be bonded to just 2 things. Incomplete octet, right? It's just got 4 electrons around it. That's A-okay. All right, it still does meet the valence electron rules. The same amount of valence electrons are present. So this compound works. Same thing with boron is going to be sort of unique because it likes to generate, when we see later, these trigonal planar structures. So boron and beryllium are rule breakers. They essentially generate electron deficient molecules. But hey, it's not bad. They still cover all their valence electron bases. And they also have good formal charge, which we'll get to in a little bit. Okay, now on the other end of the spectrum is expanded octet. So expanded octet is available to all elements in row 3 and below. So what that means is pretty much everything on the majority of the periodic table is actually able to have an expanded octet. When you first learn this, it's like the exception to the rule, because in middle school and maybe earlier in high school, you learn like, oh, it's all about that octet. And they're showing you this Bohr model. You get into AP Chem and they throw you the quantum model and they're like, oh, actually most things don't give a crap about octet. Not that they don't give a crap, is that they can have expanded octet. So expanded octet is not the exception as much as it's the more normal thing. And you're like, oh my gosh, you're ruining everything I learned. No, believe me, it's really cool. Expanded octet. So why do they have an expanded octet? Just in case you get asked, it's because they have access to the d orbital, right? So usually you think, oh, but the d orbital is like below the higher 4s. Didn't you tell me last time, for the d, just do like whatever else you have, n-1? Yeah, that's true, but technically that orbital is available to the atom to have electrons in it. So it's able to make bonds where it has more than 8 electrons around it. Now, some of them are like, you're like, well, how else could you do it? Like they like to show this one a lot for something that has an expanded octet, sulfur fluoride. Sulfur hexafluoride. So you might draw something like this. You're like, this breaks those honk rules. Yeah, I know, I get it. That's just kind of to get you started. So, and we would draw, oh my gosh, all these electrons. And if we add up the electrons, assuming each of these have 6 around them, we're going to see this is a stable compound. So that's easy when it's SF6. But what happens when it's SF4? So we're going to have sulfur here, and we're going to have fluorine. And you're like, dude, we're done. And then you realize that you still have some extra electrons left over. So this came with 6, and this came with 7 times 4, so 28. And that's going to give us 34 electrons that we're working with. And assuming we draw all these guys in, you might realize, hey, how the heck is this thing going to work? I only have 32 electrons, but everyone's happy. They got their octet. And then someone's like, what do I do? Let's put the 2 right here. And you're like, dude, that screwed up the octet for sulfur. But it doesn't matter. It doesn't matter because it's allowed to have an expanded octet. Now you might go, well, when is it supposed to have it? When is it not? You can use the valence electrons to help guide you. But the next topic we're going to talk about is formal charge, and that's going to help you as well. So just know anything below the third period has the potential to have these. Sometimes it's obvious, like SF6. That's the only way you could do SF6, I guess. But something like SF4, you have to think about like where are the actual electrons at? What's the total number? And usually formal charge is going to help you with this as well. All right, so great job. If you have issues with expanded octet, just ask your teacher, ask me, ask someone. In the end, it's not that hard to really understand, in my opinion. It's just that you were so stuck on the idea of octet and you basically cling to that worldview that when someone disrupts it, it's just very unsettling to you. So just get used to being open to all thought forms and ideas without judgment. And you might find it a lot easier to accept things like the expanded octet. Oh, I'm going to show you one that people hate. What if we do this guy? So new students of chemistry get really uncomfortable when they see a noble gas bonding to anything because you were told, again, chemistry is the course of like 10,000 exceptions. You were told, oh, noble gases never bond to anything. They are noble. They stick to themselves. Well, in reality, some of these larger ones actually can. And that's again because these atoms are so big. They have their outer shell is so large that they can actually bond. They aren't helium. They aren't like this little island. They do have the ability to interact with atoms around them. So if you see something like that, don't freak out. It's totally possible. Oh, last thing I wanted to mention are molecules that are what we call free radicals, which means that some of their electrons, not only do they have lone pairs, but they actually have true lone electrons. And this is usually going to be the case when you have an odd number of electrons. So we're not talking about NO minus or NO2 minus, which actually have an even number of electrons. We're talking about NO and NO2, the uncharged molecule. So if we try to draw one of these like NO, right? So we're going to use our little valence method. So we got 5 electrons, we got 6 electrons, so we got 11 electrons. So it's at 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11. Does that look good? Oh no, it's good. 2, 4. You're like, oh my gosh, it doesn't have an octet. It only has 7, but this one's okay. So overall, it looks pretty good. But this lone electron out here, nitrogen is just fiending for that extra electron at this point. So we call these kind of molecules where they have 1 electron, whether that is nitrogen like this. You can even have an oxygen free radical, something like that. I guess that's like an oxygen minus free radical. This is super reactive. This is going to react with something. It wants an electron so desperately. It's like, give me electrons, give me electron, give me electron. I need to complete my life. I feel empty. So these are called free radicals, and they're freaking weird because they don't follow the octet rule. They at all. They're like this weird off thing, and you might sit there for hours and say, how can I do something with an odd number of electrons? Everything on the Lewis diagrams are always in pairs. It's okay. Once you're okay with being alone, you don't have to be lonely anymore. All right. That's what I tell my free radicals. Okay. So we got NO going on right here, and that's perfectly okay. And it's really weird, but it works. Same thing with NO2. It has a free radical. So I notice these pop up a lot with nitrogen compounds. Don't be blindsided by it. This is one of those weird exception free radical compounds that don't have their octet completed. They still finish their valence electron requirements, and they still have pretty decent formal charge, which we'll see as our next topic. Again, if you're struggling with Lewis structures or you run into one you don't know, well, not only do you have all the resources of the internet to help you figure it out, there's also people like me and your teacher. So reach out for help, and I'd be more than happy to explain some of this stuff to you on more of an individual level. Okay, formal charge and resonance. Okay, this one is fun. So formal charge, I would say, is like sort of the true way to decide what the best Lewis structure is. Now, I don't know if I wasn't paying attention in class when I took AP Chem, or if my teacher just didn't teach it to us, but I never knew what this was until I took chemistry in college. And I was like, oh, now I make sense why some structures are good and some structures are bad. So we're going to take this first molecule, CO2, and we're not going to follow some of the advice that I may have said earlier about like how many they like to have, how many bonds things like to have and stuff like that. And we're going to look at 3 ways that you could technically lay this out and have a decent number of electrons. I mean, a decent number of valence electrons. Okay, so overall in CO2, let's count it up real quick. We got 4 valence, and this is 6 times 2, so 12 valence. So we got 16 electrons to work with. I've already spent 1, 2, 3, 4, 5, 6, 7, 8, because they're doubled, 9, 10, 11, 12, 13, 14, 15, 16. Ah, awesome. Actually, I think they're all going to look sort of like this, just with a different layout. I feel like there's another alternative one that I wanted to show. Maybe it's this. Or is that going to give us the wrong one? So hold up. I knew there was something. There's something special here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14, 16? Does that work? No, that doesn't have enough. Let me find a better example. Okay, we got CO2, CO2, CO2. Let me see the CO2 formal charge. Yeah. Oh, okay. Oh, Lord. Now I remember. That's what the other really gross looking one is. Okay. What if you got real freaky and you did this? Okay. I think that has enough. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 16. Okay, so these are technically all ways you could draw it. And I think this is why, especially beginning students of AP chemistry, or even regular chemistry, they're like, wait, which one works? These all match those valence electron rules you told me. They all match the octet rule. How are these not all correct? And this is where the idea of formal charge comes in. So there is a technical equation for formal charge. So formal charge is essentially I guess I call it the number of electrons around an atom that are being shared with it directly versus how many it sort of would like to have based on its valence shell. So we can calculate this by taking the number of valence electrons minus the bonding electrons divided by 2 plus the lone electrons or lone pairs. Here, I'll make those little electron symbols. Okay, so this is like the formula. I'm going to show you how I do it. I just kind of think about who's sharing what and where it would like to be. So for my first one here, carbon has 1, 2, 3, 4, and of these bonds, it's sharing part of it. That's represented by this bonding electrons divided by 2 plus lone electrons. So there's 6 here. Usually carbon has a valence of 4. So this is a lot more electrons than kind of carbon was bargaining for. So this would be like a 2 negative as what we would determine as its formal charge. Oxygen only has 1, 2, 3, 4. And we know oxygen usually likes to have 6. So valence is 6 minus, here, I'll show you how to do it down here, minus 8 bonding electrons divided by 2, since the bonds count as 2, and 0 lone pairs. So this is going to give us a value of positive 2. And finally, this last one over here has 1, 2, 3, 4, 5, 6. And it likes to have 6, so that'd be a 0. So those would be the formal charges on each atom in the compound. Negative 2 on carbon, positive 2 on oxygen, and a 0 on the other oxygen. Now this one we can go through and do the same thing. I'm going to go super fast. There we go. And that's going to be a 0. The next one is going to be that's going to be a 0. And the last one that's going to be a 0. Okay, we got a little bit left over here. So on this one, it's going to be a negative 1, and that's because there are 7 electrons it has around it. Sorry. For those of you who just go straight for the formula, you've got what? 6 valence electrons minus 2 bonding electrons divided by 2 plus 6 lone electrons. So 6 minus 7 is going to be negative 1. Okay, this one's got 1, 2, 3, 4. Hey, and it likes to have 4. So that's going to be not bad. That's going to be 0. And finally, this last guy over here has 1, 2, 3, 4, 5. It likes to have 6. It's going to be plus 1. Trying to do these formal charges really fast because this video is getting really long, but that's okay. All right, so that's what we would that's formal charge. That's how we would determine. You're like, okay, why are we doing that? Because the whole point of formal charge is the best Lewis structure, the one that's the most likely to be the official one, that the properties basically correspond with the most based on our predictions and understanding of bonding, is going to be the one with the lowest overall formal charges. Then if you do have to have a negative formal charge somewhere in the atom, you usually want that to be on the most electronegative element, right? It would make the most sense that there would be slightly more electrons around it the way that it's being shared. So formal charge is all about basically doing this calculation, determining if the structure is the most stable. You want something where the electrons are equally spread out appropriately based on the different properties of the atoms involved. So in this case, this is our official CO2 structure. And these ones are not acceptable because they do not have the optimized formal charge. Now, what happens if you do this whole thing and you have more than one structure with all optimized formal charges? And that's what we're going to look at next. That's what resonance is all about. So some students just think resonance is all the different forms. Like this would not be 3 resonance structures because they're not all viable. Resonance structures are typically they're viable, that they have the best alignment or arrangement of formal charge. Okay, so we're going to look at resonance structures here, which we're going to start with a Lewis structure, and then we are going to look at the formal charges and the different possibilities there are. So this one is NO2. So again, I'm using kind of my little strategy of how many bonds to make of 3 for nitrogen. Nitrogen can make the most bonds usually out of all these, so that's why I put it in the middle. Sometimes it doesn't work. Like oxygen here, there's no way that it can have 2 bonds. You'll see why in a minute. Okay, so something sort of like that. Okay. Let's see. Are there any other resonance structures? Well, of course, there would be that other side. So these do count as resonance. They're not identical. So just because they're mirror images, that doesn't mean they're the exact same thing. I think this is supposed to have like that. Let me count the valence electrons real quick. So we got 5 valence electrons. We've got 6 times 2 is 12. And we got one bonus one because it has a negative charge. So we're working with a total of 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, cool. So both of these are basically, they meet the valence electron rules. They meet the octet rules. Overall, they look pretty good. So I can't think of any more. I mean, of course, you could throw in some other weird stuff. You could do like this or something, right? Why not? So we got 2, 4. Okay, I'm going to throw that guy off to the side just to basically prove a point. All right, so now I'm going to find the formal charges. Okay, this nitrogen has a formal charge of 0. This oxygen has a formal charge of 0, and this one has a formal charge of -1. Oh, also, typically, if we have a structure that is an ion, we put it in brackets and we put the charge on the outside. So you might be like, wait, that has a -1 formal charge. That doesn't seem like balanced out. Oh, there's an overall -1 charge on this ion. All right, we're good. So that's another thing I may have missed saying, that your overall formal charges on the structure should be equal to the charge on the species. If it's an ion, it can have not 0, but if it's a non-charged particle, it should have a formal charge of all the atoms that adds up to 0. On this one, we got 0, 0, -1. So again, corresponds to that -1 charge. Okay, so this should be a -1 as well. But let's do some really freaky formal charges here. Ooh, this is really bad. This is not having enough electrons. This one has, how many does it have? Oh, Lord. Oh, this one's okay. This one's decent. And this nitrogen has, oh, we would have to add even more in order to make this work. So I can't even think of how I would, wait, how would I do that? Hang on. Okay, so usually if you start drawing your Lewis structure and you realize like, hey, I didn't do this right, and you have too many electrons, you usually want to turn one of the lone pairs into a double bond or a triple bond. If you have not enough electrons, you usually want to turn one of your double bonds into spread them out. So I think that is a little bit better. Is that going to work? Yeah, that is going to be our 18 electrons that we were looking for. So now I'm going to put my formal charges in. This one's going to be a little too negative, of a -1. Looks like this one here is going to be a +1, and this one's going to be a negative. All right, so you can see here, this one it still has that overall -1 charge, but it's not the most optimal way of spreading out those formal charges. Remember, you want those values to be as small as possible, and then if you do have a -1 left over, you want it to be on your most electronegative elements. So this is not a viable one based on formal charge, but these other two are pretty good. They basically are the same. They both have an even way of spreading them out. It's as optimal as we can get on the formal charge for an ion. So we would call these resonance structures. Okay, so we usually draw them out and then we draw a double-sided arrow pointing between them. Frequently, resonance structures are ions, so you might also see them with the brackets and the charge. That's not because it's resonance, that's because it's an ion. Now, what does this really mean? Like, what is the true nature of NO2 minus of a nitrite ion? And the way I learned it in college, which I personally liked because it kind of represented it better for me, is something like this. It's like a happy medium sort of between both. It's not that it's constantly becoming a double bond and single bond. It's that the bond actually displays characteristics most like what we would call a 1.5 bond. And if somehow this was being shared between like 3 atoms or something, oh, I don't think that's the one I want, like a different compound, then this bond would be more like a 1.33 bond based on its bond energy, its behavior, the overall like geometry of the molecule, all that kind of stuff is going to show that it's actually kind of like a hybrid. It's like in between. So usually you want to write it like you see up here. This is also a notation you might see, but this is typically the way that we do it. So that is formal charge. Again, formal charge is like the king of determining the best Lewis structure. Know how to do it, know this equation. If you're an equation person, think of it like I do. If you're a visual person, where you just kind of, for each bond, you kind of just count that it gets to keep half of it. That's essentially what this is representing. And then I count the other electrons. Strategy's up to you. Okay, last topic of the night. Man, this was a jam-packed unit. That's the truth. Okay, so now we've got VSEPR. If I even spelled that right, VSEPR and hybridization. Oh, I did, VSEPR. So what does VSEPR stand for? I sometimes forget. Valence shell, electron, positioning, or repulsion. I'm not 100% sure, but it basically is a theory that describes how electrons are arranged around a central atom. The big idea here is that electrons repel other electrons. They do not like to have areas of high electron density being close to one another. So essentially, these geometries are ways to optimally keep all the electrons as far apart from one another as possible. So, oh, dang it, this one doesn't have the names. I wanted to put a chart that has the names on here, but we can look at these as well. So this one would be like what? Linear. This is what we call trigonal. Planar. This would be considered bent. So there's these different names that go with them. You should know those names. This is one of those things you got to memorize. Memorizing the name shouldn't be the hardest part for you. Memorizing the angles can be sort of annoying too. But in general, if you memorize the what I call the basic geometry or the electron geometry, which is the what I also call the parent structure, it makes it a lot easier. Also, if you can get your hand on a molecular models kit, like that is probably worth more than an AP review book or an AP review class. In my opinion, you can get one for like $20 on Amazon or less. Get an actual molecule kit and connect them together and see what it looks like. Use it with your hands and your eyes. It's going to be such a better learning experience. Chemistry is already very low on opportunities to visually see a lot of these concepts. All right, but how do we actually do VSEPR? So I would say when you're first learning it, get the table out, have the table next to you, and just practice a lot. So you should do these together: Lewis structures, VSEPR geometry, hybridization, polarity, IMFs. You can basically take any compound and try to do all of those. It's going to be great practice, and you can find tons of resources online that will show you if you were right or not. And that's how you're going to get good at these, is through practice. And then the memorization will come kind of naturally as well. So how do we do it though? Let's say we take a compound. Let's take NH3 since we've already done that one. And I'm going to quickly draw it out. All right. The first thing I'm going to do to find VSEPR geometry is first draw the Lewis structure. Okay. The Lewis structure is just going to help me with it. It's not going to necessarily tell me anything about the actual geometry. So the first thing I do is after I have the Lewis structure, I count up how many electron domains do I have. I see 1, 2, 3, 4. So these are any areas around the central atom that contain electrons. These could be both bonds or lone pairs, either one. And then what we do is we go down this chart. Another name for these electron density areas is the steric number. It's kind of more old school. You might hear either one. So get a chart that has the steric numbers or the electron density numbers. And since this one has 4, we're going to go down to 4. And since it has one lone pair, we're going to go down this part of the table and we're going to go, oh, here we go. And it doesn't have the name, unfortunately, on this table, but that would be called trigonal pyramidal. It's basically a tetrahedral, and you cut the top off. So these geometries, the names, I think they kind of make sense. Some people think they're like nonsense, but I think they make sense if you think about the parent structure and then remove certain constituents where the electrons, the lone pairs are. And it does sort of make sense. If you build this one with a little model kit, it looks like a little triangle, like a little mini pyramid, because there's no tetrahedral part on the top. So again, practice, practice, practice. Use the chart at first until you get the hang of it, and then see how many you can do without. Most of the molecules you encounter are going to be up here, right? It's going to have a steric number of 4 or less. Now, sometimes with expanded octets, things can get crazy, and you can get down in here. They're way less common, and the angles are they're not more confusing. It's the same kind of numbers. It's just, you got to think about it a little bit differently. Okay, so one last thing. Where do these angles come from? So in general, the angles are based on the angles, the mathematics that make these different parts coming out of the central atom as separate from one another as possible. Remember, these electrons do not like each other. They do not want to be next to each other. So for tetrahedrals, it's about 109.5 that separates them. So you might say, well, why does this say less than 109 when it's a trigonal pyramidal? I thought you just said it's a tetrahedron with the top cut off. Well, this is super dense in electron density, right? There's no protons over there. That's just pure electrons, lone pairs floating around. They are going to have a lot more repulsive force on, not a lot more, but enough that it's going to kind of crunch that angle. So it's going to be less than 109. That's why when we look also at something like water, which is H2O, and if we draw that structure, it's going to be like that, OH, and the two lone pairs. That's going to look a lot like this guy. And this is called a bent geometry. And water, I think, has a degree angle of around 104. And why is it so much less than 109? Because these two packs of lone electrons are really applying force on the other ones and repelling them even more. So it kind of crunches that angle. What I've been noticing on AP answer keys and FRQs and multiple choices is they kind of give you a range. You don't really have to be that aware of that angle crunch. I would say on a water molecule, if you said something just like less than 109, even if you said 109, I bet you might be able to get away with it. I've seen a lot where it's just like accept anything in a range of 100 to 110. So don't stress too much on the bond angles, but you should memorize like the ones in these basic geometries, and then you can apply them to other things. All right, so VSEPR, I'm not going to explain every structure. Practice, practice, practice. Get a model kit. Look at some kind of 3D models online or something. All right, we're almost done. A couple last concepts here. We got another exception statement. And this says molecular orbital theory is recommended as a way to provide deeper insight into bonding. However, the AP exam will neither explicitly assess molecular orbital diagrams, filling of molecular orbitals, nor the distinction between bonding, non-bonding, and anti-bonding orbitals. Man, I remember learning this in college, and I was just like blown away. It was very confusing for me to understand the first time I learned it. There are anti-bonding and non-bonding and all this like complicated things about how the S and P orbitals and the sp3s and sigmas and pi's all come together. You don't have to know it. So don't freak out. If your teacher was a little crazy on you and taught you about anti-bonding orbitals, just let it all go. Okay. What do you need to know about these sigma pi things? Well, if you're interested in geometry, it is pretty cool how it works. And it does explain why a double bond is not flexible and a pi bond is not flexible. But do you really need to know it? No. What you really have to know for the test is this. Sigma bonds is a single bond. If you have a double bond, you still get your one sigma, but you also get a pi bond. Okay? And if you have a triple bond, you're going to have one sigma bond and you're going to have two pi bonds. Pi bonds are bonds made between p orbitals, and since they're perpendicular to the plane, they kind of like lock into place, and they're very hard to spin. Whereas sigma bonds are like s orbitals or hybridized orbitals, and they kind of can spin and turn. That's why if you ever play with those molecule kits, single bonds, you should be able to rotate freely. So what do you need to know about sigma and pi bonds? This is pretty much it. They might ask you how many sigma bonds are in this molecule, how many pi bonds, that kind of stuff. Just know this association. It's going to be 98% of what you got to know. All right, one last topic, and that is hybrid for the night, which is hybridization orbitals. Again, there's some like massive exception statements here. The first one is basically that you don't need to be able to derive or depict how hybrid orbitals look or fit. You don't need to know those pictures. Also, you don't have to bring up the hybridizations of things with the steric number of 5 or 6, which is basically going to be things that involve sp3d or sp3d2. That is outside the scope of the AP exam, so do not stress on that. So what is this hybridization thing? Well, in reality, if you want to make 4 single bonds, if you want to make 4 sigma bonds, and you don't have 4 bonding s orbitals, then the molecule says, that's okay. We'll just kind of like mix and match the s's and p's so we can get what we want. You're like, that does not make sense. Okay, here's what you need to know. If your steric number is 2, or if you want to say your electron density is 2, or electron density areas, it's going to be sp. If your electron density areas or your steric number is 3, it's going to be sp2. And if it's 4, it's going to be sp3. Now, these examples are a little bit misleading because they don't tell the whole picture. They're like, oh, yeah, it has 3 things bonded to it. So, but here's an example that throws a lot of people off. This one has 2, it's linear. This one has 4, it's sp3. Let's look at H2O. Right, we already modeled this. So the Lewis structure is right here. You should be able to see that it has 1, 2, 3, 4 domains of electrons, which means that's a steric number of 4. So what kind of hybridization is an H2O? sp3 hybridization. You're like, wait, it only has 2 bonds. Shouldn't it be sp? No, it's not about the number of bonds. It's about the number of electron domains. It's about the steric number. Yes, water is sp3. Guess what else is? NH3. Even though it's trigonal pyramidal, it has 4 electron domains, even though one of them is filled with electrons. So that's going to be an sp3 hybridization. CH4, they already have that example in there. It's going to be sp3 hybridization. So this is, again, they don't want you to know the details. It even says that right here. It's like, we just want to be able to ask you what's the hybridization and you tell us. And they love this. This is one of those topics that comes up all the time. Along with IMFs, PES spectra, they always ask you something about hybridization. It's going to be on the test, along with electron configuration. So this is super easy. Just put it along when you're studying your VSEPR and you're doing the VSEPR, Lewis structure, polarity, IMFs, all that stuff together. Make one other little box on your little worksheet or on your paper you're doing it on and add hybridization. Now, there's a lot of cool chemistry in here, and I wish I had the time to explain it, and I really hope you learn it someday. But if you're just trying to pass this test, that's all you got to know, right? Number of steric number or number of electron domains is going to be directly connected to the hybridization value. And that is it. We made it through it. Man, that was a long video. I know I got a little long-winded at times, but hopefully that helped. If anyone tuned in live, then thanks for tuning in live. If you're watching this later on, that's cool too. Good luck. I will try to get another video up soon before next week because I am about a week behind right now. But if you enjoyed the video or you found it helpful, tell a friend, like, subscribe. If you felt it could be more helpful, if you have any kind of feedback or if there's specific individual support that would help you get ready for the AP test, feel free to reach out to me and I'll do whatever I can with my time and my resources to help you succeed. That's all I'm really trying to do here is just provide free help, free support, and free services to anybody who needs a little bit of extra hand on the AP Chem test or is feeling a little bit overwhelmed right now. Okay, with that, I'm going to wish you a good night and I will see you